This is video 1 of the quantum mechanics mini lecture series. I'm gonna call it historical context part 1. So I'm going to try and cap these videos at a maximum of 5 minutes. Okay. So our journey begins around, let's say, 1860 onwards. So the latter half of the 19th century. And what happened during these years was that scientists, particularly in Europe, was studying the light given off by different elements, okay, in their gaseous state when heated. And I'll show you the just a simple schematic. This isn't really what they were doing exactly, but it's just sort of to give you an idea of what was going on. Let's suppose you've got a gas, an elemental gas. Okay, let's say it's sodium gas. And let's suppose you apply heat to it. Okay, so let's suppose the scientists heated up some sodium gas using a Bunsen burner. What happened was, as expected, light would be emitted from the sodium gas, okay? And they then passed it through what's called a collimator. Okay, to collimate something means to make something straight, parallel. Okay, also known as a slit. Okay, to create a parallel beam of light. And you would get a parallel beam of light going through, followed by a prism, okay, a glass prism, a glass material. And what that would do is that it would give, in the case of sodium, special colors. Okay. So let's say I'll draw an eye here. Okay. Okay. So the scientists would see for sodium two very specific colors of light, yellow in this case. Okay, and then obviously there'd be an eyepiece here, okay, like the eyepiece used in a microscope or a telescope. Okay, or it could be a photographic plate in this case. This device here is also known as a spectroscope. Okay, a spectroscope is an optical instrument designed to analyze emitted or absorbed light from a substance. Okay, in this case, sodium. So it's very simple. You heat up some sodium gas and you look at, and you split up the light into its constituent colors, which in this case is yellow, and you would see it through an eyepiece. Now, this was very puzzling. Why? Well, because from the sun, let's say I'll draw like a, let's suppose this is a photographic plate. Let's suppose we're looking at the sun's light. Now, from everyday experience, if you've got like a piece of glass on your table at home, like a decoration, and you let in sunlight into the room, and it goes through the glass, you'll see like a rainbow, right? I'm not going to draw a rainbow, it'll take forever. Okay, but the rainbow, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Okay, that's the rainbow, that's what's expected. What wasn't expected, what scientists found, let's suppose we've got a photographic plate here. For sodium, for example, they would see two very specific colors, okay, two yellow lines. Okay, so in this case, they found that sodium only gives off very specific colors, okay? Very distinctive, what are called wavelengths. Distinctive, so very specific wavelengths. And what's a wavelength? I'll define that right now. Okay, and also I should also mention this is all black. Okay, why is it black? Because sodium only emits at those two colors. That's why you get a black spectrum here, okay? Sorry, a black background, okay? So a yellow spectrum against a black background. So light is known as a transverse wave. What's transverse wave mean? Looks like this. Okay, it goes up and down, up and down. Wavelength is the distance between the two peaks in a light wave, okay? Also a peak is called a crest, okay? And the dips, also called troughs, okay? Could be also the distance between two troughs. That's a wavelength. And you've got things like the amplitude for a light wave, which is how high it is, how much energy it has. So for sodium, it's got two distinctive wavelengths at these particular numbers, these particular values. Okay, nanometers, nm. A nanometer is 10 to the minus 9 meters, a billionth of a meter. So they're very short wavelengths. Very short means very high energy. High energy means you can pack more peaks. So that's what puzzled scientists in the 1860s onwards.